In this week's EOS Friday, we're going to be taking a big leap going from single component systems to mixtures. First, we'll see how nature does things, and then we'll try to reproduce this using the flash calculation. Following this, we'll define our mixing rules for the EOS parameters A and B, and then we'll discuss how do we pick the correct root from the equation of state to get our volumes. And finally, we'll take a look at what's coming next week. Let's get started by a nice little animation of the flash. Let's say we have a container with some initial volume of oil at its bubble point. Increasing the volume, we're going to get gas out of solution. Once we reach the desired pressure and temperature, we'll have a certain volume of gas and a certain volume of oil. Using this pressure and temperature and the total feed composition, this is going to be our basis for the flash calculation. The output of the flash is going to be the equilibrium compositions Yi for the vapor and Xi for the liquid. Using the equilibrium compositions and the EOS, we can plot the EOS curves for both phases. In this case, we're using the van der Waals equation of state. However, for what we want to do, we actually want to rearrange the equation to be on a cubic form with regards to the Z factor. We see that the vapor part has a single root, while the liquid part has 3 roots. By picking the correct root, we can use these Z factors to get back to the volumes of liquid and gas in the container. This is in essence what the flash calculation does. So let's take a look at that in a bit more detail. So we started with an initial composition pressure and temperature. We can utilize the composition together with an estimate of the K values in the Ratchet-Rice solution, and this is going to give us our equilibrium compositions. If you haven't checked out the previous video series on the Ratchet-Rice equation, make sure to check that out. With the equilibrium compositions, we can use a set of mixing rules to give us the vapor and liquid EOS A and B parameters. Now these are really important because we can use this together with the EOS to give us the fugacities of each phase and also the volumes or Z factors of each phase. We're not going to discuss now what the fugacities are or how to calculate them, but what you need to know is that they're used in checking whether or not our fluid system is in equilibrium or not. If this is not the case, we update the K value estimate and repeat the loop. However, if the fluid is found to be in equilibrium, we take our equilibrium compositions and the Z factors as the true compositions and volumes. Now that we have this overview of the flash calculation, let's dive into the mixing rules and how we define them. Naively, you might expect the average A and average B just to be the same function as the component A and component B using average values for the critical properties. Now, if you're interested in more details about this topic, then I would really recommend reading up on it. It's very fascinating, but also very challenging. Now, the actual mixing rules were first introduced by van der Waals himself. However, most modern EOS models usually have a correction term to the mixing rule for A, which contains the binary interaction parameters Kij. Now, the most common mixing rule for B is just a straightforward linear mixing rule. Now, it's important to emphasize that even though these are the most common mixing rules, they are by no means the only mixing rules that you can use. This is a whole area of research, and there's a bunch of different mixing rules that perform better or worse depending on the situation. But for our use, these 2 mixing rules are more than sufficient. Moving on to the next topic, we want to see how we can pick the quote-unquote correct solution for the Z factor. Plotting the cubic polynomial versus the Z factor, we see that we have 3 possible solutions. The first thing we want to do is remove the middle root because Michelson proved that this will never be the true solution. Now the way we're going to pick the Z factor is going to be based on which of the 2 roots gives the minimum Gibbs energy. Now we're not going to go into the details of why this is the case, but this is what we're going to do. Now we're left with only 1 root and we can continue on with our flash calculation. So what are we going to take a look at next week? Well, next week is going to be the last video in this little mini-series. And we're going to try to discuss some of the aspects of lumping our EOS model from a more detailed composition slate to a less detailed composition slate while trying to maintain as much of the accuracy as possible. All right, until next week, thank you for watching.